All right, let's get started, guys. Today, the topic is influence maximization and cascades on or in networks. So we actually previously, on previous lectures, we discussed different viral propagation properties, right? We talked about how virus spreads around. In fact, news and rumors can spread in a similar fashion, right? When you have information, it propagates along the edges and it spreads on the contact. And then, depending on, for example, the length of the contact or your familiarity with the person, there is a bigger or smaller chance for you to gain that information, right? So the same way as with virus, the chance of you getting virus depends on the strength of the tie, depends on the virality of the infection, and of course, structure of the network. When we talked about virus propagation, we considered three different models: SIR, SIS, and SI. Well, in fact, even more models, but that's where the main models, and one can also adopt them to describe news information. Now, today we're going to talk about slightly different models of the diffusion of information, or actually diffusion of, often it's called innovation on the network. And the reason is the following. Quite often, when we want to consider certain processes, we can think of nodes on the network as agents that make their own decisions, right? So, if we're thinking about the viral propagation, this is usually about, the probability of contacting a virus, and you're not making a decision of, getting infected or not getting infected, or if somebody comes and tells you some rumor, some news, you're not kind of making a conscious decision whether you want to hear it or not, you're just being told. Well, imagine that the agent or a person in the network, in the social network, can in fact make decisions, right? Whether to, accept something or not. The idea here would be, you can talk about, for example, adoption of innovation. Let's say, you want to decide whether you want to, I don't know, buy a new iPhone or not, or switch from one model to another, or switch from one telecom operator to another, or maybe joining political protest. And in many cases, it's going to be about the behavior of your friends, right? Because let's say, if all of your friends joining political protest, you most likely will also join, versus if nobody joins, well, there is less chance for you to join. And so if you think about it that way, you realize that certain actions, they actually spread along the network. And the probability of a person participating in this action depends on his connections, right, on the connectivity patterns. And though each person has his own sort of decision rules, whether it's sort of join or not join, the behavior of the entire system will strongly depend on a structure of the network. Okay. So in this sense, there's a sort of microscopic changes in the behavior can lead to macroscopic results, the changes of the behavior of the entire system. We're going to actually be focusing more today on the notion of, adopting of innovation. But, you can think about many other things where there's this cascading behavior can be observed in the network. Now, this adoption or diffusion of innovation goes back, the studies goes back to like 1940s, previous century. And it's what's called Ryan Gross study of hybrid seed corn. It's sort of historical study back then. Of course, and then has been a lot of other studies conducted, but this is one of the first one where the farmers were given some information about the new type of corn. And then, and this is 1924 when this new type of corn appeared, and the histogram showing the percentage of the farmers who know about it. And notice that there is this sort of spike in 1930, 1931. That's when information spread around it, but people would not plant that corn back then. And the reason they didn't want to adopt this innovation, and one of the reasons, they wanted to see it in action, and they wanted to see, for example, their neighbors or friends using it. And so it shows you that there is this two different types of processes. One type of process is this hearing of innovation, another type is adopting it. And though this is the same friendship network, in one it's the information that spreads, and another it's adoption that spreads. And the adoption, you can see here, it's spread with significant delay, so it had different mechanism behind it. And so the question is, how does it work? Well, imagine that we're looking at the network, and there is this node W right here. Let me try to annotate. Okay, so this is a node W in question, and there are neighbors. It has it connected to these 4 neighbors. And this node wants to choose some sort of optimal behavior that depends on the behavior of its neighbors. Imagine situation, the following situation. Let's say, you're using mobile. Let's say this is your 3 friends, right? And this is the only friends you have. And you're using, say, MTS, mobile operator, and your friends are using, say, Megaphone. And then the question is, well, should you stay with MTS or should you switch to Megaphone? And obviously, each operator provides you sort of free within the operator calls. The obvious answer, yes, definitely you should switch, because then you will be able to talk for free with your 3 friends. Now, but then the question is, okay, well, if one of the friends is still on MTS and 2 others on Megaphone, should you switch or not? Right? The answer is also trivial, but you need to compute it, because depending on the cost of each or per minute for each line, it can be optimal for you to stay or to switch. And that's the idea of how you can judge, how you can discuss this type of approaches. So we can make it a little bit more formal by invoking what's called invoking the ideas from game theory. And this is called the local interaction game. There are players, and each player has a strategy. And each strategy has a payoff. Now, payoff means, if you play the strategy and the opponent plays another strategy, how beneficial it is for you. So payoff is a benefit you get for doing certain actions. And game theory, the entire game theory is really about your performance against the changing world. So it is your action versus the action of your sort of opponent player. Okay. So the idea is the following. Let's say we have 2, and it's usually the payoffs usually written in the payoff matrix. So if we have 2 players, U and V, and both, for example, adopt behavior A, let's say they're both using Megaphone, then the payoff to each of the players is little a and little a, right? Now, if both players adopt behavior B, let's say they're both using MTS, then the payoff or the benefit from both using the same technology, the same operator is BB. But let's say, if one stays with one provider and the other stays with another provider, the benefit is 0, right? Because you'll have to pay for the calls. And, the same way if you do it, opposite. So that's sort of the idea. Now, if we really want to calculate things, let's see how good we can do it. If I ask you to make this type of judgment, this type of a decision, and let's say, the benefits of being on one mobile operator versus another one are equal, in the sense of the costs for you, then the obvious answer is, okay, if more than half of your friends are on one operator, well, you probably should switch to that one because calls with them will be for free, right? But then, if the costs are different, right, the benefits are different, the payoff are different, then, the balance could be shifted. It might not be necessarily half of the friends, it can be different portion of the friends when you need to make a switch. Like, for example, looking at this slide, if this node V in the center, if the node V in the center needs to make a decision, then which sort of strategy to play, right? Strategy A or strategy B. Then it really depends on the portion of his neighbors that use one strategy or another, and the payoff of each strategy. For example, if the payoff for strategy A is A little, then P is a portion of the friends, D total number of friends, and payoff on one side joining strategy A will be that, and payoff on the other side will be that. And then you can actually calculate the threshold for the central node to select the behavior, or A or B. Now, if the payoffs are equal, then we're going to get here 1 divided by 1 plus 1, right? It's 1/2. So the threshold is 1/2, which means, if more than half of your friends using one particular strategy, that's the strategy you want to select, right? Except the behavior when you exceed the threshold. So there's sort of quite obvious conclusions, but this is a nice and clean way of getting them. Now, we discussed this sort of one-step process, right? We have a node that can change behavior based on the neighbors. But what's interesting is how this behavior propagates across the entire network, right? Because let's say there is a node that changes behavior. Let's say there is this node, by whatever reason, changes the behavior, adopts a new strategy. So what about these nodes? Should they change their behavior or not? And shall we consider it in a one-step or two-step moves? Well, look, if, for example, we consider the changes of the behavior the following way. Let's say the payoff on the strategy A is 3, the payoff on the strategy B is 2. So strategy A is actually preferred. And then the threshold, the way we defined it in the previous slide, is going to be 2 divided by 2 plus 3, so 2/5. What it says literally is if the more than 2/5 of the neighbors are switching to a new strategy, well, the other node should also switch to that strategy, right? So then the question is, okay, let's see, how this might play out. Let's say again we choose this node W, and let's say this node changes strategy on its own, right? By whatever reason, again, you can think here about, switching from Apple to Android, switching from, one technology to another technology, switching from one, from one mobile operator to another. It's probably the most obvious example. So let's say that node switched, but the threshold is 2/5. So we can go and look at each node surrounding this guy, and we'll see. So with node B, it is one of 3 nodes that switched, and so it is 1/3, while threshold is 2/5 of the neighbors should switch for this node to switch. So it's not going to happen. Well, the same thing for node S, for example, or node R. So if there is only one node that switches strategy, nothing is going to happen. There's not going to be any sort of propagation of this new strategy on the network. But now let's imagine that by some reason, in fact, there are 2 nodes that switched the strategy at the very beginning. Maybe they had some monetary incentives, or by whatever reason, there is these two nodes that switch the strategy. Then what happens is, let's look at node S, for example. Node S still has only 1 out of 3 neighbors with switch strategy, and so node S doesn't want to switch its strategy. But if we look at the node R, this node has 2 out of 3 neighbors that switch the strategy, and we have the threshold 2 out of 5. So 2 out of 3 is, of course, greater than, 2/3 is greater than 2/5. And that means this node should switch its strategy. And the same thing in this one. But then on the next sort of iteration, the next step, now if you go back and look again at this nodes, all of a sudden, 2 out of 3 neighbors has new strategies. So now this one will have incentive to switch strategy, and this one will have incentive to switch strategies. And so that's what you see here, right? So, and that's the picture, that's how you need to look at it. So what's going to be happening is you're going to get a cascade. There's going to be a sequence of changes of strategies of the players. And yes, there'll be some very particular order in this sequence, in these changes, because some of them will have on a different time step, on a different step, there will be different number of neighbors, and so there'll be different incentive to switch or not. Now, when we're talking about cascade, it's a one-way street in the sense that the node is allowed to change strategy only sort of one way. You're not allowed to go back within this type of modeling, right? But this shows you how this sort of new strategy, new behavior propagates. And now you can think about, again, adoption of innovation, or switching to a new mobile operator, or anything of that kind. Let me stop here for 1 second. Does this make sense? Do you have any questions on this?
Is there any way to model different influence of the nodes? Because right now, as far as I understand, we are aggregating the neighbors equally with equal weights. But in real life, it may be that the decision of one of your friends is more important for you than all the others.
Good point. Just wait a little longer for a couple more slides, and we'll generalize this approach to actually include different weights on the edges. You're absolutely right. You can actually encode, for example, the influence, the strength of the influence, right, into the strength of the edges. Right now, this is just sort of the idea. Okay. So one other thing that was worth noting, that those type of cascades will not necessarily, spread and cover the entire network. That's made this huge difference in between this model and versus the virus propagation model, right? Whereas, for example, in the SI model, inevitably, eventually everybody gets infected. So here, there is a possibility for cascade to stop. Now, why would this happen? Well, if you look at this slide, you realize that even if we start a cascade with this, start the cascade with this 2 nodes, right? You can see that, for example, for this guy, there is this 2 nodes, the neighbors, so this guy is going to switch. For this guy, these 2 nodes are neighbors, is going to switch. Then on next iteration, for this guy, 2 neighbors will switch. This guy, 2 neighbors will switch. Next iteration, this guy, 2 neighbors will switch. But then when it comes to this guy, well, it's only 1 neighbor that is red. So it will stay with the original strategy. So nothing is going to propagate here. But even if we take these guys, you realize that for this one, there is also 2 links to all the strategy and only 1 link to a new strategy. So there's not going to be switch. And the same here. And so that means these guys will also all stay with old strategy. So that's the final picture. And so even if we seed with new strategy 2 nodes here, the influence region will stay that way, right? And you can observe that that might happen because, well, either they're only sort of weak link to other connected sets, or maybe there is quite enough density here that it's not allowing to propagate. But the main point is that structure plays critical role in here. Now, of course, if the threshold changes significantly, and it will be even more beneficial to join new strategy. For example, we set up threshold as 2 out of 5, but let's say if the threshold is 1 out of 5, then of course it will propagate everywhere, because say, even for this guy, it is going to be 1 out of 3, which is greater than 1 out of 5. So this is, we'll switch the strategy, and then this will switch and this and this guy, and so on. So 2 parameters. So one thing is a threshold, obviously. The other is the network structure. But with certain combination of the threshold value and certain type of network structure, the propagation of the cascade will stall, and the cascade will not cover the entire network. And then sort of there is this obvious question that comes up into mind is that, okay, well, can we actually calculate, can we predict the size of the cascade, or the size of the number of the nodes that will switch their behavior? And even more interesting question, can we actually optimize it? Can we actually find that seeds those nodes that we need to seed with a new type of behavior, such that the cascade, the number of converted to new behavior nodes will be maximum. And that's quite obvious question for example, for marketing. If you,
excuse me.
Yes.
Andrei has a question in the chat about Cascade.
Yeah, well, can I see chat? Give me a second. Under the condition of experience update of Cascade, can 2 different orders of update lead to drastically different results? Yes, you're absolutely right. You can actually, you can have different results depending on where you start your cascade. Now, but if you start, if that's what you're asking, depending on where you start your cascade, which nodes you start with, you might get very, very different, very different cascade results. Now, one important point here is that, I'm sorry, I was talking about the marketing guys. Well, for them, the question is, imagine that this is a social network. This is a, say, call network, and this is the people who call each other, right? And let's say you actually want to kind of make an inroad into your competition and try to convert people into your, to switch to your mobile operator. Well, one of the ways of doing this would be, okay, you need to find a group of nodes, the seed nodes, that you somehow may convert into, into using your mobile operations, and then hope that, based on this cascade, their friends will start switching to you, right? And their friends will start switching, of course, if it's going to be profitable for them, and it's going to be profitable is if they're sort of the right, or if there is enough friends already switched before. So, the first comers can be converted by, providing, I don't know, free plans for a year, or maybe, giving them free phones or something. And you do this, and then you expect that you give this free stuff to just a small number of people, the seed nodes, but then the cascade of this influence will propagate and make everybody else eventually to switch. Well, not everybody else, but a lot of people to switch. So that's how this can be used in practice. That's why this problem got a lot of interest from marketing people. Okay, so but that was sort of quite sort of a toy problem, right? So it was sort of conceptual story. And in fact, this type of approach was for the first proposed by and discussed by Granotter and Schilling in like 70s. Now, if you want to make it more sort of computable, applicable, we need to put this into some more sort of stable framework. And the paper, which usually being referred to as a sort of founding paper on this topic, is a paper by David Kempe, John Flyberg, and Yves Tardash from 2003 on influence propagation. And they proposed two models. Well, in fact, this model has been known before them, but they kind of collected them and proved a few theorems. So one model they called an independent cascade model. It's so-called diminishing return model, where, and we're going to talk about each of the model in turns. And the other one is the linear threshold or critical mass model. So the independent cascade model, or the model of diminishing returns, it's the way the influence acts on the nodes. So in that model, each node can influence, can be influenced by the neighbor, and the more nodes are neighbors, the higher the influence, right? And the other model is this threshold model, where there is no effect from the neighbors until you get some fraction of your friends, and then it's you turn the switch, and then you're affected, right? So again, one is sort of slow growth that says your sort of participation or your activity, the chance of your activity is proportional to the number of neighbors, and the other one says, okay, nothing happens until the threshold reached, and then you flipped. So how do you actually make this model work? So the first one is this independent cascade model. The idea is, and both ideas, of course, this is just sort of a more technical approach to what we already discussed. So we have initial set of active nodes S0, and then we model things through discrete time steps. And on every step, an active node, right? An active node, this is sort of infected node, if you wish, right? The active node, or the node that uses uses new approach, right? New technology. And an active node can activate, in fact, connected neighbor with some probability, right? So there is this active node. I'll draw it bright red. Then there are neighbors. And then a node can activate its connected neighbor with some probability. If this V, this is W. And this probability can, of course, depend on the edge strengths. This is pretty much the response to one of your questions. Yeah, can we do it with a different edge strength? Yes, of course. And now, if this activation happens, the node W becomes active on the next time step, right? This becomes active, this remains active. And let's say this guy has also, two nodes, and there is some probability on the next time step that will activate this one or activate this one. If that happens, there is this 3 active nodes. And, the process runs until no more activation possible. In fact, this model is very, very much similar to the SIR model, but where node stays infected only for one step, and then then converts into R. In this case, R also means active, right? And if also all the probabilities are equal, right? So if all probabilities are equal, and we just allow one chance for a neighbor to infect the neighbor, In SIR model, you can infect it all the time, right? Here, we're just giving only one chance. Then it's pretty much SIR model. Alternatively, linear threshold model, this is explicitly models the threshold behavior. So the situation is the setup is similar. There is this node, and it has neighbors. And then there is an influence on each link, and each node has some acceptance threshold. So this node has some acceptance threshold. Nothing happens if there are only a few nodes that are active, and then there is a threshold when things start happening. And we can actually have exactly the same threshold for each node, or we can make more interesting and make it make different thresholds for different nodes. But the point is that we need to have fraction of active nodes to exceed that threshold. So we take the sum of weights on the active nodes, and it should be greater than the threshold. Going back, if to our toy problem, all the weights back then were ones, right? And here we just put some weights, and then the sum of for the sum of the weights for, say, 2 active nodes has to exceed threshold, and then they'll activate this neighbor. And then this process iterates on the discrete time steps. And again, it's progressive, which means you go one way, non-active to active, right? So that's the mechanism. And this is pretty much a generalization of what we discussed at the beginning of the lecture. All right, so what can we do with this? Well, first of all, you can actually just literally take and run this type of process on different networks. And for example, this is an example of this type of cascade model run on a random graph. Now, I want you to remind that in the random graph, we had this parameter p times n, and here it's called z, which is the average number of neighbors for every node. And when it was 1, that was a threshold for random graph to get a gigantic connected component. All right. Now, phi here is a threshold, and threshold can be smaller or larger. And on the left slide, we have a threshold which is homogeneous. So we take a random graph and we'll put threshold that is homogeneous. We choose this threshold which is the same for every node. And notice what happens. Let's say I pick up some value of threshold 0.14. Now, of course, there is nothing happens until we reach the value z equal to 1, because this is a disconnected graph, right? You're not going to get cascade. But then there is an entire region. So what happens if we go along the z-axis? The graph, the random graph, becomes more and more dense, right? Because this z is probability of nodes being connected times number of nodes. Or average number of neighbors for node, right? So average number of neighbors, 2, 4, 6, 8, 10, etc. So notice what happens. Then there is this region where you get this global cascade, and global cascade means that the entire graph eventually being covered, converted into the new, technology, right? Becomes active. But then if you actually have a denser graph, there'll be no global cascades. And the logic is the following, that when you have very dense connections, you will not have enough neighbors converted to a new strategy, to convert U, right? So there's this interplay in between where you need to have enough density for this to spread, but not too much density such that you will still have enough new behavior, enough nodes with new behavior in the neighborhood to convert a particular node, to convert U in this behavior. And of course, the larger the threshold, right? The larger the threshold, the more difficult it is to convert to new behavior. The narrow is this region where it is possible to have a global cascade, right? So if the threshold is pretty high, you will never get global cascades. Now, this is just numerical experiment run on a random network, but it's quite telling. And on the right slide, on the right-hand side, on the right picture, it's exactly the same type of experiment, but it is in this case, instead of fixed threshold, there is a normal distribution of thresholds per node. So each node has a different level of threshold, and that, of course, the sigma is the width, and that, of course, changes this whole behavior, changes the region where cascades can happen. Now, when there is a large distribution of the thresholds, it means there are stronger thresholds and smaller thresholds, you start getting cascades, almost everywhere. And in fact, that also tells you, for example, if you think about, we talked about this at the beginning, say political uprisals, or where different people have different thresholds to the chain, to the behavior. Some people will go on the streets, only when most of their friends will go, and some people, need only one or two persons, and they will go. So with this wide range of the wide width of the distribution, wide range of thresholds, it's very easy to actually get a cascade where then the entire system flips. Okay. So here is an example from a different paper, but it just shows us, some networks. On the first network, some empirical network, BSC, some random network. The red dots are initial seeds, and then you see that with certain selection of seeds, you get cascades, global cascades when everything is flipped. But with other set of seeds, you don't get that global cascade. And so then the question is, okay, well, if we want to get global cascade, what conditions should be satisfied, or how should we select nodes to get the global cascade? And that's precisely the formulation of so-called influence maximization problem. So the way it's set up is the following. We have an initial set of active nodes, A0, and the cascade size is the expected number of active nodes when the propagation stops. So, we start this process, we iteratively step-by-step activate nodes, but eventually, we ran out of opportunities, and, we ended up with some cascade, and this is a cascade size, which is 1, 2, 3, 4, 5, 6, 7 in this case. And so the question is, find the set of nodes, and it's, we look at the K set of nodes, which means, okay, find, set of 5 nodes, or find a set of 10 nodes that produces maximal cascade. And this is called K-set maximum influence nodes. And this problem is actually hard because, as very often in discrete optimization problems, you end up needing to go through all the possible combinations, and that's computationally prohibitive. So, but that's the problem setup. That's the problem you want to be able to solve. So you want to find initial set of nodes to have the maximum size of cascade. For example, here I selected these 2 nodes as initial set, and we got the cascade of size 7. The question is, if I take, say, these two nodes, what would be the size of cascade? Maybe it will be larger than 7. Or if I take, maybe this node and this node, would the cascade be larger or not? And so the question is how to choose that optimal set of nodes that will maximize the cascade.
Excuse me.
Yes.
If we start cascading from same nodes, but with different algorithms of spreading, is the result always the same?
Different. What do you mean? Different algorithm of spreading? Different parameter sets, or
No. You just, sometimes you show firstly upper nodes. Sometimes like I don't know, using DFS or BFS, like this. I don't know how to say it right in this case.
Okay, so okay, let me understand. So you're saying if we select the different rules of activation, in this case, I assume you'll get this. If you select the different sequence, right? Because I go, I start
sequence maybe it's right or
no, you should be able. We should be able to get to the same. With the same threshold parameters, we should get to the same result with the same threshold parameters and the same set of rules here. Okay, now in order to actually solve this problem, and again, guys, the actual problem here is that it's just too many combinations, right? Because ultimately what you want to start your cascade. Let's say if I want I don't know, 3-set cascade with 3 nodes, then I need to go through all possible 3 nodes combinations, right? It can be these 3 nodes, or it can be 1, 2, 3, and that's obviously C3 out of n how many combinations I can do. And if I want to cascade of size 5, that's how I need to do it. And then I need to start and grow the cascade. So it's just too many combinations to deal with it. But there is a trick, there is a solution to this. And the solution is based on this notion of submodularity of this function. The function that we actually have, the function, the cascade size function. Now, so what's some modularity for a set? It's a notion of the concavity property of the function, or in other words, diminishing returns. So what I'm trying to say is the following: imagine that you have I'll draw this way. Let's say we have one set and then we have another set. Actually, let me do it. Sorry, let me clear it. So we have one set and we have smaller subset of this set, right? This is S and this is T, right? And so submodularity means the following. Now imagine for each of these subsets, for S and for T, there is some particular function, some particular value that you can get. Again, it's cascade size. So the idea that if you increase the function, the size of the set by adding, say, new element, then the effect of that increase will be larger for a smaller set. So the difference in between adding a new element to a set is larger for a smaller set than for a larger set, right? When the smaller set is a subset of this larger set. So it's this notion that whenever you add things, you get more changes at the beginning, right, when the set is small, and less at the end. And that's called submodularity when you talk about the set function, or it's, in economics, it's going to be diminishing returns, that, the further you go, the larger the scale, the function will be, will have less and less slope, right? Adding more will produce less results. And it has been shown that the function that has this property, that monotone submodular function, has a very interesting property. And the property is the following: that if we know the set, the optimal set that maximizes our function, right? Then there is a way to build a greedy set S by certain very simple rule, and we're going to discuss this rule. And in the result, the value of the function for that simple set, for the greedy set, will be not worth than 1 minus 1 over E of the exactly maximal solution. So this is a perfect solution that you can get, right? That comes, let's say, from Oracle, that this is the best you can do. But to get that, we need to solve an NP-hard problem. What we're saying, this theorem saying that instead of solving NP-hard problem, you can actually do some greedy process. And when you do this greedy process, and greedy process means it's polynomial time, you do this greedy process, you're not going to get a perfect result, but the result you're going to get is not worse than this times perfect result. So, and this number is, I believe, 0.63, right? 0.63, you can calculate this easily. So you're not going to do worse than that. But so you're paying the price, you're not getting the best, but you do it in polynomial number of steps versus NP-hard that needs to get the exact answer. And this process is really very simple. It just says that on every step, you just need to select an element that produces largest marginal increase. So if you do that, this is a greedy process that, some finite number of steps, polynomial process, you get the solution, not perfect solution, but you get it pretty quickly. Does this make sense? So we're replacing exact solution, which is NP-hard, with approximate solution and with a way to construct it in a greedy fashion. As a result, it guaranteed that this greedy process will give us solution not worse than 63% of the best solution by value. Okay, so if best solution can give us sort of the largest value of a cascade, by using this greedy algorithm, we can get a cascade at least the size 63% of the maximum possible cascade. Now, what's this greedy process? Oh, here it is, right? So I actually talked about it, but it's 0.629, right? So greedy algorithm will find a set such that its influence is within 1 over E from optimal set. So what's this algorithm? It's actually just brute force greedy algorithm. Very, very simple. What we do is we actually pick up a node and then calculate the influence from that particular node, one node, all right? We're going to get some influence. You pick up another node, calculate the influence. You go through all the nodes, calculate the maximum influence from that node. After you're done, you select the node, the first node that gave you the maximum influence, and you fix that node. Then you take that node and you pick up the second node. The first node is fixed. And then you go through all possible second nodes. And for each pair for each second node and first node, you calculate the maximum influence. And you find and you pick up the second node that gives us the largest influence with those two guys. Then you fix those two, you pick up the third one, you go through all the possible positions for the third node to give you marginal increase, you pick up that one, and so on. How is it different from just trying to maximize it, the NP hard way? Well, the NP hard way would be, okay, well, you need to go through all possible combinations of all three nodes, right? That's the difference. Here you do the first one, you fix it, it's n steps because there are n nodes in the graph, right? Then you go for the second one, it is n-1 nodes that you need to cover. Then you go for the third one, it's n-2 nodes. And pretty much you just need to do this, k times is the set that you want to find consists of k nodes, right? So that's literally it. That's the greedy optimization algorithm. And based on the theorem, it guarantees that this approach will bring you up to 63% within the reach of optimal solution. Any questions here? All right. So here's examples. Okay, so first of all, let's just go back actually for a second, and think about sort of other ways to solve this problem, the influence maximization problem, right? One way would be to just say, okay, look, I just pick up randomly, some nodes and, run the activation from those nodes and see what happens, right? And here is the results of this random simulation. You take, let's say, 5 nodes randomly, pick up 5 random nodes, it actually activates, well, almost 5 nodes. You pick up 15 nodes, also not getting a lot of activation. You pick up, I don't know, 30 nodes, you also get almost no, when you randomly pick up nodes, they usually don't come close together and usually cannot start a cascade. But then you can think of like, okay, well, let's think about some different heuristics that might be useful. You can actually assume some other things, some other properties of the nodes that can affect the size of the cascade. What kind of properties can you think of? Will the degree of the node that be a good property to select the node to see the cascade? Well, it could be, right? Because high degree node has a lot of neighbors, so it can influence a lot of nodes. Or maybe you can think about centrality, right? If the node is central to the graph, it's sort of in tactical position, such that actually strategic position such that it can affect a lot of nodes. Maybe that's a good that's a good choice for initial seed node. So based on those heuristics, here another curve. There is you pick up 5 most central nodes. Well, that's the size of cascade you get. You pick up 20 central nodes, this is the size of cascade you get. Or maybe you take a high degree nodes, and if you take 10 high degree nodes, that's the size of the cascade you get. Or there is also page ranking. There are many ways you can do this. And then this is the solution. This is a greedy algorithm, that the one that we described. So it actually wins over any other sort of heuristics approach for size of the cascade. So actually here we looked for dependent cascade, here we look for linear threshold models. In fact, the behaviors of the models are different, right? In one case it's threshold, in another case it's probabilistic, the activation, the behavior is quite similar. So that just tells us that yes, if we want to maximize, the greedy algorithm is the right thing to use. So it's not always that if, for example, you want to convert most of the people from one, say, cell phone, from one mobile operator to another, well, you don't necessarily need to give, free phones to people who has most connections, right? But there is still different strategically selected nodes that might be optimal. Now, the catch, of course, is that though it is still optimal from the point of view of algorithms, unfortunately, it's still computationally expensive, right? If you have a large seed set size, and if you have large number of nodes, it's still large network is still computationally expensive, because you need to go through the first node and you need to calculate all the influences, right, for the entire graph, propagate step by step. Then if you take the second one, you need to do that again. You take the third node, you do it again. So it's still a lot of computations, and there has been a lot of work in trying to speed them up, and by proposing some sort of shortcuts, by reusing some computations. And obviously, since we're computing on the same graph, there is an opportunity to reuse some kind of computations. There's also questions of sort of trade-offs, right? Yes, random computations, randomly selecting nodes is the stupidest thing to do, but it's the quickest thing to do, right? But then, if your graph is sort of pre-processed, you do have, node degrees, so it can be extremely quickly to, rank nodes by the degree, versus notice, this is if you do, some sort of greedy approaches, right? So this is 10 to the third, and this is, 10 to the minus third. So, there is a difference of 6 orders of magnitude in computational time, of course, for this particular graph set. But there has been a lot of activities in terms of, speeding up those algorithms and proposing sort of new approaches, some hybrid approaches that uses some heuristics and then this greedy optimization approaches. And so, today, those algorithms actually, used in practice to calculate influence in networks. And with that, we're done today. Here are some references. I think here is, there is this last reference here is 2009. There were actually a couple more recent reviews, like 2018, also on influence maximization in networks. You can Google them; they're easily available online. In the 9 years since 2009, there was a bunch of algorithms proposed that actually do the same thing, but they do it much faster. Okay. Any questions? Let me see. No questions. All right. Thank you, guys. And you'll have a seminar a little bit later today. Thanks. And bye.
Там вопрос в чате.